Hi, this lecture notes is to accompany day 2, where we talk about linear programming. I'm not going to discuss any further the linear inequalities where we shade in. We're going to use that skill to do linear programming. Linear programming is where we model a situation with an objective function or an optimization equation, sometimes called. And you'll have certain restraints or constraints that give you a feasibility region on a graph. And from that feasibility region, that means that any of those things inside the feasibility region could satisfy the equation. But usually you're looking for a maximum or a minimum of the equation. So the thing to remember is to separate the objective function or the optimization equation from the feasibility region, which is where you look at the constraints of the problem. And when we graph this, we might have a triangle, and the top point does not make it a maximum. The top point could be a minimum, or the bottom point could be a maximum of this function. But each one of the vertices of our region will be either the maximum or the minimum of our objective function. Let's try one and you'll see what I'm talking about. Here are 3 constraints, and this last piece is the objective function. So this is the objective function right here. Now I'm going to pull over to the side. I've actually graphed this using Desmos, and so you can see this red section is this first equation. It's y is greater than or equal to, and the y-intercept is 4. On the second equation, y is going to be greater than, that's going to be this blue region, which is all of this. And the third part is where it's less than, it's going to be down here. So this dark brown region is the area that is my feasibility region. Any answer within this area will satisfy all 3 of these equations. But I want to know which one is going to be a maximum and which one is going to be a minimum. And so I need to take the vertices and substitute them into the optimization equation. And I'm going to do that. You get f of, we get f of 2, 3, or 0, 2. F of 0, 2 is equal to 3 times 2 plus 0. We get f of 2, 0 is equal to 3 times 0 plus 2. We get f of 4, 3 is equal to 3 times 3 plus 4. Well, this is 9 plus 4 is 13. That's going to be the maximum. Here we have 2, and here we have 6. So this would be the minimum. 2, 0, minimum, and 4, 3. And it just happens that it's the highest on the graph. That is not always the case when you plug it into the function. Looking at the next one, here we have 2 different blends of coffee to be made. 75 pounds of Colombian. So we have Colombian and we have Brazilian coffee available. And we have 120 pounds. We also have blend A and blend B. Blend A and blend B. Blend A will have 4 ounces of Colombian coffee and 12 ounces. Now, since we're using ounces, let's convert this to ounces. 120 times and 75 times 16. 75 times 16 is 1. 75 times 16 is going to be 1,200. So this would be Colombian. You could have 1,200 ounces of coffee beans, and then you have 120 times 16, which would be 1920 in Brazilian total. Now for each blend, we're going to have 4 ounces of Colombian and 12 ounces of Brazilian for blend A, and it'll be 8 and 8 for blend B. And we're looking for the profit, and the profit is how many ounces of A I make times 0.2 plus the B, which is times 0.38, And that's going to give me my maximum profit. We want to maximize the profit. So this is our optimization equation. What are the constraints? We have, if we call this x, we have 4x plus 8y is equal to, or has to be less than or equal to 1200. Those are the Colombian beans. We have 12x plus 8y has to be less than or equal to 1920. And we also have, you can't have negative things. So our x value is going to be greater than or equal to 0, and our y value is going to be greater than or equal to 0. And x is going to stand for the A, and B is going to stand for the B. Y would be for the B. I've graphed this using Desmos, and I'll pull it over to the side so you can see it. Here we have it. And you can see I have 3 numbers to explore. And when you plug these into this equation, you get your solution, which is going to give you the maximum amount. And in this case, it's going to be the 90 and 105. And you can substitute those in and see this for yourself. In the third problem we have, store owner wants to limit the payroll to $9.60. Employees get $4 an hour, or overtime they get $6 an hour. And for the company, they make $18 for regular work, and $32 is how much profit they will get off of overtime work. We're also restricted that the overtime hours are restricted to 2/3 of the regular hours. So we want to maximize the profit. The profit is going to be $18 for the regular hours plus $32 for the overtime hours. That's going to be the number we're trying to maximize. We want to find out which value will give us the optimum here. So I know that I have $4 an hour for the regular plus $6 an hour for the overtime. And that's got to be less than $960 because that's all the money I have to pay out every week. And I also know that my regular time, 2/3 of my regular time was what the overtime will be. Now, if we let the one value equal to x and the other y, I've graphed this once again using Desmos. And so let me choose my selection tool. And you can see the values come in between these 3 constraints. And I also said that I can't do 0 hours. So I also put in, so if I have this is x and this is y, x, excuse me, this is my x and this is my y value. This is my x and this is my y value. I also have x's to be greater than or equal to, this has to be less than or equal to, greater than or equal to 0, and y has to be greater than or equal to 0. When you substitute these vertices, which is where the feasibility region comes in, into this optimization equation, you will find out which one is your optimum. And I think that it's this one. I'm not sure. I'm pretty sure it's this one. So that's what I've got for you today. If you have any questions, just bring them to class tomorrow. Thanks.